The paper introduces LLMatic, a novel neural architecture search (NAS) algorithm that leverages the coding abilities of large language models (LLMs) and the robustness of quality diversity (QD) algorithms. It aims to automate the design process of neural networks, a major challenge in deep learning. LLMs have shown significant capabilities in generating code when fine-tuned on code datasets, making them an attractive tool for generating diverse and high-performing neural architectures. The authors argue that current NAS approaches, such as reinforcement learning and evolutionary computation, can be quite inefficient and wasteful, requiring the testing of thousands of architectures. By combining an LLM with an evolutionary algorithm, LLMatic seeks to inform the search process using stored knowledge about how to design neural networks. This approach could potentially lead to more efficient and effective NAS. The proposed method is tested on the CIFAR-10 and NAS-bench-201 benchmarks, demonstrating competitive performance with only 2,000 candidate architectures evaluated, without prior knowledge of the benchmark domain or exposure to previous top-performing models. The open-sourced code for LLMatic is available at. Large language models, LLMs, have limitations when applied to neural architecture search, NAS, particularly in generating diverse and competitive neural networks. To address these limitations, this study proposes LLMatic, a novel approach that combines the domain knowledge of code-generating LLMs with a robust search mechanism. LLMatic leverages quality diversity search, specifically the map-elites algorithm, to efficiently search for competitive networks. By doing so, it achieves a significant reduction in the number of evaluations required, with just 2,000 evaluations needed to generate a set of competitive networks. The authors emphasize the importance of generating a diverse set of architectures that vary across relevant dimensions, such as parameter counts or depths, to understand trade-offs and make better informed decisions. Additionally, they highlight the value of considering model complexity as a diversity metric, searching for high-performing models of varying sizes. The LLMatic approach begins with a basic neural network and utilizes a dual archive cooperative quality diversity optimization. This involves storing neural networks and their corresponding code generation prompts in separate archives. The fitness function for networks is based on test accuracy, while the prompt archive uses a curiosity score to select prompts and temperatures. By combining the strengths of LLMs and quality diversity search, LLMatic provides a more effective and efficient approach to NAS, enabling the generation of diverse and competitive neural networks with minimal evaluations. The LLMatic approach is a novel method that leverages neural architecture search, combining the capabilities of large language models and quality diversity optimization. This innovative technique begins with an initial network and a random prompt, which undergoes mutation operations to generate new variants. These network and prompt individuals are then evaluated and stored in separate archives, based on their performance. The evolutionary loop of LLMatic involves crossover and mutation operations, where the best networks and prompts are selected based on fitness. This process continues for a set number of generations, allowing for continuous improvement and adaptation. To evaluate the effectiveness of LLMatic, the CIFAR-10 dataset is utilized. Ablation studies are conducted to demonstrate the benefits of each component in the approach, providing insights into how different elements contribute to the overall performance. By refining the neural architecture through this evolutionary process, LLMatic showcases its potential in enhancing the efficiency and accuracy of language models. The LLMatic algorithm is a novel approach to neural architecture search, initiated by initializing a network and prompt archive. It proceeds with a generation process where networks are either mutated or undergo crossover. The algorithm evaluates the generated networks and updates the archives accordingly. A key aspect is the use of quality diversity optimization, specifically CVT-MAP elites, to ensure a diverse set of architectures. The setup includes the CIFAR-10 dataset, a simple initial neural network, and specific parameters for training and evolutionary operators. The algorithm's ability to automate the subdivision of the archive and find nearest neighbors is particularly noteworthy. The neural architecture search process employs large language models, LLMs, and quality diversity optimization. It involves settings for minimum and maximum flops, encoding of prompts, and selecting networks and prompts based on curiosity scores. CoGen, an LLM, generates neural networks trained on datasets like the Pile, BigQuery, and BigPython. An ablation study evaluates the impact of components such as network archive LLMatic, prompt archive LLMatic, mutation-only LLMatic, crossover-only LLMatic, and random NN generation. Each component is found necessary, with mutation-only LLMatic and network archive LLMatic performing closest to LLMatic, and crossover-only LLMatic performing the worst. The study compares the algorithm's performance with efficient NetB0, highlighting the efficiency of LLMatic in finding competitive networks with fewer evaluations. The evaluation of LLMatic's performance across various generations showcases its efficiency and accuracy on CIFAR-10. Figure 2 illustrates the best accuracy per generation for LLMatic and its ablation studies, demonstrating a consistent improvement. The shaded region represents standard deviation, while the solid line indicates the mean accuracy. This is accompanied by the introduction of archives, specifically the prompt archive and network archive, used to store and select high-performing neural networks. Figure 3 visualizes these archives, highlighting the diversity of high-performing networks in the network archive. The discussion then focuses on the choice of probabilities for crossover and mutation, concluding that mutation should be given more probability. The experimentation is further extended to the NAS-bench-201 benchmark, detailing the structure of the cell block and the main body of the skeleton. Neural architecture search has been revolutionized by the introduction of LLMatic, a novel approach that leverages large language models and quality diversity optimization. By harnessing the capabilities of large language models to generate diverse and high-quality neural architectures, LLMatic evaluates their performance on various image classification datasets. This method employs a prompt-based approach, where curated prompts guide the generation of architectures within the model. Quality diversity optimization is also utilized to ensure the generated architectures are diverse and of high quality. Experiments were conducted on 3 image classification datasets: CIFAR-10, CIFAR-100, and ImageNet 16120. LLMatic was compared to several baseline methods, including random search, DARTs, lambda DARTs, and Genius, a GPT-4-based NAS algorithm. The results show that LLMatic outperforms the GPT-4-based NAS baseline and achieves near state-of-the-art performance, although it exhibits more variation than competing methods. An analysis of the distribution of networks discovered by LLMatic over each generation reveals that the distribution of found networks is spread wide in the search space, demonstrating the exploration capabilities of LLMatic. This research presents a new paradigm for neural architecture search, leveraging the power of large language models and quality diversity optimization to generate diverse and high-quality neural architectures for image classification tasks. LLMatic is a novel neural architecture search algorithm that combines the capabilities of large language models with quality diversity optimization algorithms. This approach enables the discovery of competitive networks that exhibit diverse architectures, achieving near-optimal performance on NAS-bench-201 with a remarkably low 2000 evaluations. The efficiency of LLMatic is attributed to its utilization of a 6.1 billion parameter language model and a reduced population size per generation. A comprehensive ablation study reveals that each component of LLMatic is essential for its performance, highlighting the synergy between the large language model and quality diversity optimization. The study demonstrates that the algorithm's effectiveness is not solely dependent on a single component, but rather the integration of both elements. The successful application of LLMatic raises opportunities for future research directions. A natural extension is to compare LLMatic with other neural architecture search methods on various tasks, providing a more comprehensive understanding of its capabilities. Furthermore, exploring the potential of LLMatic for open-ended learning could lead to novel insights and breakthroughs. The paper introduces LLMatic, a novel approach to neural architecture search that leverages large language models and quality diversity optimization. It explores the potential of using large language models as a source of inspiration for neural architecture search, demonstrating how these models can generate diverse and high-quality neural architectures. The method combines the power of large language models with quality diversity optimization, aiming to find a diverse set of solutions that maximize both quality and diversity. Tested on several benchmark datasets, including ImageNet, results show promising improvements in performance and efficiency compared to traditional neural architecture search methods. The paper provides an extensive review of related work, highlighting the importance of understanding the role of large language models in this context. It emphasizes the need for further research on leveraging these models to enhance efficiency and effectiveness. The authors discuss limitations and assumptions, as well as potential avenues for future work, including training custom models and exploring other optimization techniques.